Hello, and thanks for using TickBoom. Here a student has asked me to help with answering the question, find the locus of arg z minus z1 on z minus z2 equals beta. So I've drawn up an argand diagram here because I think ultimately that's where it's going to be easiest to reflect what the locus would be of this. But I think the best place to start here is to notice that we've got these 2 points, these two complex numbers z1 and z2, which we're going to hold static. And then we're asked to find the locus of the complex number z. How would that move in the argand plane if this rule has to be true, that the argument of z minus z1 on z minus z2 equals beta. So a natural place to start would be to just plot these 3 points that we're dealing with, z, z1 and z2. It doesn't really matter precisely where you put them because we're not specifically told what their definition is. So I might just start, I'll put z here. Maybe I'll put z1 here. And maybe I'll put z2 here. It really isn't critical where you put them. But the first thing to note is that when you connect these points, so if I was, for example, to connect z to z1, that line I can think of as a vector, and I can pick a direction such that this line, I could say, represents z minus z1. And the same deal with connecting z and the point z2. I can say that that line can represent z minus z2. So from there, it's then helpful to think of what is the argument of each of these lines, which if we know the argument is the angle that the line makes with the real axis. So if I just kind of come up and just draw a kind of equivalent parallel line with the horizontal axis, we know that this angle, I'll call it alpha, that's the argument of z minus z2, and this angle here, maybe I'll call it gamma, because we're already using beta, so that's going to be the argument of z minus z1. Now, something that you may not think to do but will be helpful is if I were to just extend these lines all the way down to the axis, what we see is we end up with a triangle, and this angle here will also, these angles will be the same because remember this is parallel to the axis, so this will be alpha and this will also be gamma, this angle here. And what I can say is that this is the exterior angle of a triangle, and I know that the exterior angle of a triangle is equal to the sum of the two interior angles. Hopefully that's a result that you're familiar with from earlier math. So therefore I can conclude that this gamma is equal to alpha plus this angle here, this kind of angle from z, the angle z to z, z, and then z1. So that angle there. So if I do a bit of rearranging, I could then say that the gamma minus the alpha is equal to the angle z to z, z1. And now I can kind of rewrite in what I'm dealing with. Gamma is the argument of z minus z1, and alpha is the argument of z minus z2, and that's going to be equal to this angle here. And so I can then write this as the argument of z minus z1 on z minus z2 is equal to this angle. Now, given this is in the exact format of the question, I'm just going to say, well, let's call this angle here beta, just so that I don't have to keep writing this out. So let's say beta. So now what we can see is in the argand diagram, visually, this condition will be true when the point Z basically is part of this triangle, and if you hold Z1 and Z2 steady and you were to move Z, the question is what locus would it follow? Now, there's a general result. Hopefully you're familiar with it. That's my attempt at drawing a circle. If you were to pick 2 points on a circle, in our case there's Z1 and Z2, that's just what we'll call them, and if you've got a point here, that angle, beta, if you kept moving this point Z, but you keep the Z1 and the Z2 static, if you move it around the circle, actually the angle beta stays the same. And that's true no matter which point you pick on the circle. So what we can conclude is that if the argument of z minus z1 on z minus z2, if that always has to be fixed at some angle beta, then essentially the shape that will be curved out will be a circle between the point z1 and z2. So I'll do my best at drawing this. It's probably going to be a hatchet job, but it's basically this black line that I've just drawn here. That is the locus of Z if we have to keep this condition true. So I think that is the way to tackle this question. It's essentially the movement around a circle between the 2 points. So we don't keep going and fill the circle, but keeping this angle fixed means that we're going to end up with this shape. Now how, I mean, that question, it might not jump out to a lot of people that that's how you could tackle it. I mean, for me, having seen similar questions, I kind of knew. I've seen a question where Z1 and Z2 were just, I think they were kind of 1 and -1, so they kind of hit on the real axis, so there's no need to extend the lines. But either way, regardless of what Z1 and Z2 are, you can make use of this exterior angle of a triangle result, and then you realize that basically this format, this arg equal to a static angle, you get from a triangle. And from there you go, okay, well, it's basically a triangle move. As Z moves, we're going to keep this triangle, but if the angle has to stay the same, then we make use of this result. And this might not be a result you're familiar with, but it's one that you should become familiar with, because in this case it's come in handy. It's helped us work out the locus. So hopefully you've been able to follow along with that. I'd encourage you, if you're not familiar with this result here or this result here, to go and do some research and get familiar, because they will come in handy as you deal with these locus questions. So there you have it, and tick boom.